In this video we're going to look at the last main topic on trigonometry in A-level maths. And we're going to jump straight into an example from the booklet. It says express 3 sin x plus 4 cos x in the form Rsin x plus alpha. So before we start this, let's just think about what on earth is going on here. Okay, now if we look at our graphical calculator and we sketch 3 sin x plus 4 cos x, look what happens. Can you see that when you add a sine wave and a cos wave together, the resultant answer is actually just a single sine wave or a single cos wave? And one thing you have to realise is this is like a really useful technique in A-level maths. Like, if we've got two separate trig functions, it's much easier if we write it as a single sine function. And like, think about how the transformations work. Like that r there, the number in front that you're multiplying by, it's just a stretch in the y direction, and the alpha inside is just a translation of if it was, say if it was x plus 30, the translation would be minus 30. So all we're trying to do on this topic, this last topic, is combine sines and coses into a single sine function or into a single cos function. And you can see that it is going to become just one wave, and we just need to, all we need to do is figure out, well, what's the value of r, what's the stretch, what's the translation, and instead of working with these two separate things, we can work with this one sine function. Now, if you might not be able to see this, if I zoom in a touch, I can just see from sketching that the maximum value this goes up to is 5, and the minimum value it goes down to is minus 5. Okay, so that, just from the graphical calculator, I could see that r is going to be 5, because sine usually goes up to 1 and down to minus 1. So if you multiply by 5, it'll go up to 5 and it'll go down to minus 5. And the translation that we've moved it by is, well, it used to go through the origin, so we've moved it, clearly we've moved it a little bit. I'm not going to estimate that from the graph. Let's see how we do it by actually doing the maths. Okay, so the first thing to realise is if the form that has been given to us is sine of x plus alpha, we're going to be using the identity sine of a plus b. And maybe you'll spot this straight away, like the coefficients are 3 and 4. Oops. Bleep pen not working. The coefficients are 3 and 4. What's the link between 3 and 4 and the value of r that we saw from the calculator, which was 5? Okay. If you look on the handout, there's a proof about why this works. I'm not going to go through it. Okay. All we need to do is first of all realise that if we want to figure out what r is equal to, it's the square root of these coefficients, 3 squared plus 4 squared. So it's just Pythagoras to figure out the value of r, and that will be 5. Okay, so I would always recommend to look at your coefficients, figure out what r is first, just by using Pythagoras. Then once we've found r, we'll use this identity, because it's x plus alpha, so we'll use a plus b. Okay. So a really important point to realise, right, is this 3 sin x plus 4 cos x is exactly the same as this sine function. Okay, so we're trying to compare the original form with this new form, and we can't compare these two things straight away. We've got a little bit of work to do on the right hand side. We know r is equal to 5, we may as well substitute that in. And if, instead of having sine of x plus alpha, if we use the identity for sine of a plus b, so here obviously a would equal x and b would equal alpha, we will end up with sine of a, so sine of x, cos of b, so cos of alpha, plus cos of x, sine of alpha. So remember, this thing on the left hand side is the same as this thing on the right hand side. Let me just write it out. I'm going to write it in a slightly different way, you'll see why in a second. If I expand this out, I've got 5 times by this. You know when you multiply 3 things together, so 5 times sine times cos, you can times them in any order that you want. I'm going to put the 5 and then the cos alpha and then times by the sine x at the end. And if we expand this out, we've got 5 times by cos x times by sine alpha. I'm going to write that as 5 sine alpha cos x. Okay, the reason why I'm doing that is what we've got to do. Okay, I know there's a lot going on here, guys, but we'll do a few of these. First of all, do Pythagoras. Second of all, use the identity. And then the third step, compare what's on the left-hand side with what's on the right-hand side. So if you look at this, on the left-hand side, we've got 3 sine x's. And on the right-hand side, we've also got some sine x's. So we can say, well, if there's that many on the left and this thing is the same, however many we've got on the left must be the same as what we've got on the right. We can also do it for cos as well. There are 4 cos x's on the left and there are some cos x's on the right. And the technique's called equating coefficients. We only need to do it for one of them. We can do it for both though, for the first one. So if I equate the sine terms on both sides, I've got 3 on the left, I've got 5 cos alpha on the right. And that gives us an expression. Remember, all we're really trying to do is figure out, to answer this question, we need to figure out what's alpha and what's r. What's our stretch? What's our translation? Okay, so we'd get 3/5 equals cos alpha. Take cos inverse. Is this in degrees or in radians? It doesn't say in the question. The answer on the sheet's in degrees. I'm going to do it in degrees. In the exam, it will tell you what form to use, or whether it's in degrees or radians, if the form is given to you. It'll be obvious if you work on degrees or radians in the exam question. So if we take cos inverse of 3/5, we get 53.13. Okay, if you want to check, just while we're doing the first example, if you compare the cos terms on both sides, so there's 4 on the left, how many cos on the right? 5 sine alpha. Then 4/5 would equal sine alpha. If you do sine inverse of that, you'll get the same answer, 53.13. You can check if you don't believe me. Okay, so we've answered the question. Like, well, have we answered the question? It says express it in the form. So therefore, we know that 3 sine x plus 4 cos x is exactly the same as r, which is 5 sine of x plus alpha, which is 53.13. And that is really, really useful. You'll see why in a couple examples to follow. We'll use this form for the rest of the question. Okay, we'll go a bit quicker for the next one. We're going to write it in a different form. Now, obviously, r is going to be the same. R is equal to the square root of 3 squared plus 4 squared. So r would equal 5. But the form is going to be cos x minus alpha. Okay, so we'll say, well, 3 sine x plus 4 cos x must be the same as r cos x minus alpha. So I'm going to write that as 5. And if we write it as cos x minus alpha using cos a minus b, that'd be cos x cos alpha plus sine x sine alpha using this identity. Let's go a bit quicker. So if we just equate both sides, how many cos x's are on the left? 4. How many cos x's are on the right? If we expand this out, 5 cos. So 5 and cos alpha are multiplied by that cos x. So that would be equivalent to 5 cos alpha. 4/5 equals cos alpha. And if you take cos inverse of 4/5, we have got 36.87 to 2 decimal places. And that's all you need to do in terms of like an example style question. Like, find the value of r, use the identity, equate, figure out what alpha is, and therefore write your answer, 5 cos x minus 36. 0.7. Okay, second example, or example 6 from the booklet. Express 2 cos theta plus 5 sin theta in the form r cos theta minus alpha, where r is greater than 0 and alpha is between 0 and 90, so we want an acute alpha, an acute translation to one decimal place. Obviously we're going to be using cos of a minus b as well. Okay, so first thing I'll do, figure out r, coefficients of 2 and 5, so 2 squared plus 5 squared, that would be square root of 29. And then we could write 2 cos theta plus 5 sin theta. We know that's going to be the same as this form that we're trying to get it to. So root 29 cos theta minus alpha. So if we use the identity, that'd be cos theta cos alpha plus sin theta sin alpha. Equate both sides. Let's do the cos thetas. So how many cos thetas are on the left? 2. How many cos thetas are on the right? Root 29 and cos alpha. Don't forget the cos alpha. The whole point of us doing this is we're trying to find alpha, isn't it? So that would be what we multiply by the cos on the right and that on the left. So if we take cos inverse of this, it's 68 point, how many decimal, it's a 1 decimal place, so 68.19, 68.2. Please highlight this. Okay, a really common mistake that people make when they do this topic. It's like you've done the work on part A, you know that 2 cos plus 5 sin is equivalent to this, but then it asks you something else in the question and people sort of go, oh, this is a new question. It's not a new question. Like, we're being asked to solve 2 cos plus 5 sin equals 3. And it's a pretty innocent looking equation actually. Like, you might look at that and say, oh, I've solved equations like this before. It's got cos and it's got sin. But you can't turn this into a tan, and you can't use any of the identities, like none of them are squared, okay? So it might look like something you've done before, but actually it's very different to what you've done before, okay? Okay, so what we're going to do, we're going to use the form that we know and solve that equation instead. So we've got root 29 cos theta minus 68.2, and we're going to say when does that equal 3? And we've just got a single equation with cos in that we can solve. Okay. Before we take cos inverse, get cos on its own. So cos theta minus 68.2 equals 3 over root 29. Take cos inverse. We get 58.145. Let's go 15. 360 minus, because we've taken cos inverse, we get 303.85. We want our answer to be between 0 and 360. Now, be careful, this is a bit of a sneaky one. We're about to add, like to solve for theta at the end, we're about to add 68.2. If I add 68.2 to that one, it's actually too big. So doesn't mean we totally discount it, like we still can get another answer. Don't forget, once you've done the 360 minus answer, you can then add or subtract 360 to get multiple solutions or other solutions in the interval. And actually, if we subtract 360 from that one, that would give us 58.13. 15. Minus 360 from that would give us 56.15. minus 56.15. And then we just add 68.2 to get our two answers. Well, actually just noticed, I have to be careful with the rounding here. I've used a bit more accuracy, because if I round it twice, the actual answer we want is 12.1. But if ever they rounded it to 5 and then rounded it again, the 5 would make it round up to when we round finally to 1 decimal place. So we should be getting 12.1 and 124.3. Okay, example 7. Similar start, we've just got to write it in a certain form that's been given to us. So we've got 12 cos theta plus 5 sin theta, and the form is cos theta minus alpha. So we can see that r would equal, we've got 12 and 5, that's another Pythagorean circle, it'll be 13, but we'll do the calculation. Square is 12 squared plus 5 squared, and that'll give us 13. So we know that 12 cos theta plus 5 sin theta, we're going to compare that to this form, which I'm going to rewrite, 13. If we use cos A minus B, we get cos theta, cos alpha plus sin theta, sin alpha. And then just equate on both sides. We'll do the cos thetas again. So we've got 12 cos thetas on the left. You might want to expand this out. You've got 13 and cos alpha times by cos theta, so that'll be 13 cos alpha. And then if we divide, take cos inverse. Let's see what we get for alpha. We're in degrees again on this one. Yeah, we are. Okay, 12 over 13. So we get 22.6 degrees. Okay. So we know that from part A, we know that if we've got 12 cos theta plus 5 sin theta, that's the same as 13 cos theta minus 22.6. Okay, so part B says find the maximum value of r theta f of theta, which is 12 cos plus 5 sin, and the smallest positive value of theta at which it occurs. Now you might, when you first see this, you might think, oh, maximum stationary point, should we differentiate it? You could do that, but there's a much quicker way of doing it if we just realise that we've got this form here, which is really useful on this topic. Okay, now I've drawn it on the graphical calculator, so I've typed in 12 cos plus 5 sin, and remember we just get like a single wave. Now the maximum value, you can clearly see that the maximum that we're getting is going to be 13, isn't it? Because it's been stretched up to 13. Cos on its own has a maximum of 1 and a minimum of minus 1, but if you times it by 13, the maximum would be 13, the minimum would be minus 13. And if you do G-solve maximum, it tells you the maximum is 13, and the smallest value of positive value of theta at which it occurs, so this value where it occurs here, we're getting 22.6198, so 22.62. So the maximum occurs when theta is 22.6, and the maximum value itself is 13. So technically we would answer this question just from the graphical calculator, but let's actually see the method behind it. Okay, so I could just state max value of f of theta is clearly just 13. Like, they'd expect you to understand that. Like, the maximum value of cos is 1, so if you times it by 13, the maximum value is 13. When does it occur? So this occurs when? Oh, when? Occurs when cos of theta minus 22.6. So we get the maximum because the cos function, the function itself varies between 1 and minus 1, so the maximum occurs when cos is equal to 1. So if you take cos inverse, you would get 0. 360 minus answer, let's wait for another one just in case we get 360, and then theta would equal 22.6, 38 2.6. So the smallest smallest positive value where we get our maximum is 22.6. You can see from the graph that there's actually the maximums occur every multiple of 360 after that. If you start 360 on, most of start 360. But the answer that we get, the first positive one, is 22.6, and the maximum value is just 13. If it asks what the minimum value is, the minimum is minus 13, and that would occur when the minimum would occur when cos is equal to minus 1. So you just solve a slightly different equation. Okay. The last example, example 8, I'm going to leave. The only difference is there's a 2 theta thrown in instead of a theta. Don't use any double angle identities, just use the form in part A. And then instead of x, you've just got 2 theta instead. And there's answers provided, so just use them to check. Okay, so you should be ready for most of exercise 2. Just steer clear of question 5 and 6 because I've got to do another video on integration for that. But try question 1, 2, 3 and 4, please guys.